Hello everyone, my name is Zixuan Ma. I'm going to introduce BAGUALU, training a brain-scale neural network on over 37 million cores. This is a collaborative work from Tsinghua University, Damo Academy, Alibaba, Zhejiang Lab, and Beijing Academy of Artificial Intelligence. Pretrained model is a typical AI application and is widely adopted in multiple fields, including computer vision and natural language processing. A recent work, AlphaFold, uses pretrained models for protein structure prediction, introducing pretrained models to the field of life science. In recent years, pretrained models have been growing large, from 110 million size GPT in 2018 to 8.3 billion in Micron language model in 2019, and 3 transformer of 1.6 trillion in early 2021. The model size is 4 orders of magnitude large. A consensus of the Academy is that the larger the model is, the better capability it has, and we are far below the boundary of model size. Therefore, training large models becomes an important scientific problem. Unfortunately, training models at this size is so hard that trivial clusters are no more capable for a greater amount of computation power being demanded. So, how can we scale up to an extremely large-sized model? Top supercomputers have been fast evolving in recent decades. Thanks to the development of HPC, we are seeing the dawn of exascale, an excellent opportunity for large-scale models. The converging trend of AI and HPC is shown in the Golden Bell Prize in recent years. Multiple HPC and AI applications are awarded, such as the deep learning model for climate analysis in 2018, and the machine learning-based molecular dynamics in 2020. We are expecting more revolution brought by AI plus HPC. Now, we have our brand new supercomputer ready for the revolution. The newest generation of Sunway supercomputers processes a mixed precision float throughput of 5 EFLOPS with 96,000 nodes and over 37 million cores. Besides, we have over 9 petabytes of high-speed memory. This is the perfect machine for training large-scale pre-trained models. Our target is to push the scale of pre-trained model to a brand new level, brain scale. 100 trillion is the magnitude of the number of synapses in a human brain. It will be a milestone that we can train a deep neural network that rivals the size of a human brain. Transformer is the basic structure of modern pre-trained models. Its major components include embedding layer, self-attention layers, and feed-forward layers. Most of them are mainly involve matrix multiplication computation, which is ideal for acceleration with parallel techniques. Due to the limited memory and computation power within a single node, distributed training is mandatory. To enable distributed training, multiple strategies are proposed. The most popular ones are data parallelism and model parallelism. In data parallelism, the model is duplicated with different training data over different nodes and introduce or reduce during optimization. Therefore, it can increase training throughput or samples per second. Model parallelism partitions the model into different nodes and use the same input sample. Model parallelism will introduce or reduce or all-gather communication in forward and backward, which means that a larger model can be trained. Mixture of experts is the state-of-the-art technique for large-scale models, which enables scaling up the model size without introducing too much computation for each sample. If we simply increase the size of a small model to create a large dense model, there is much computation for each training sample. MOE employs many small models. We call each of them an expert. A special model called gate is responsible for selecting a few experts for each input, Only the selected experts are activated, and their results are added up as the output. As a result, MOE can scale model size and throughput at the same time. Compared with dense models of similar size, MOE models have higher accuracy within the same training time. This is a threading technique that has already shown strong power in creating large models. Commonly, we distribute training MOE models by placing different experts on each worker. Different batches are also placed on different workers. The gate is duplicated, so on each worker, the gate can select the target expert for each training sample. After that, an auto operation is performed to send the samples to the expert. To train a super large model on a super large computer, there are a lot of challenges. We identify 5 major ones. Choosing a proper parallel strategy, partition models, struggle on mixed precision training, facing load imbalance on MOE models, optimize on 3-way architecture. The first challenge is on the parallel strategies. On the newest 3-way supercomputer, the network is connected as a fat tree with oversubscription, which is common in supercomputers. A supernode consists of 256 nodes interconnected at a high bandwidth. However, across supernodes, the connection is much slower. Besides, there are many parallel strategies involving various collective communication operations, such as all-reduce and all-to-all. It is a large combination space to hybrid multiple strategies. A proper strategy is demanded to cope with the oversubscripted network topology. We address this issue using a hybrid of MOE and data parallelism. When we use a single parallel strategy, it commonly involves global communication. Because of the oversubscripted network topology, plus the huge number of processes, it is poorly efficient. Our hybrid parallelism strategy targets at avoiding these performance pitfalls, with higher throughput, stable for extremely large-scale models. So we keep one strategy within a supernode to utilize the bandwidth. Then we have to choose between 2 semantic mappings. Within a supernode, should we map all reduce of data parallelism or all-to-all of MOE parallelism? To settle this, we build a performance model and analyze the communication traffic with bandwidth. As a result, we select the first mapping. We perform data parallelism within a supernode and MOE across supernodes. According to our experiments, this choice is 1.6 times faster than the other one. The second challenge is that we should store the 100 trillion scale model in distributed memory, so the model has to be partitioned. Let us first calculate the storage size we need for a model of 1 trillion parameters. The model parameters needs 4 terabytes, the gradient needs 4 terabytes, the optimizer parameters need 8 terabytes, and the intermediate needs about 8 terabytes. So partitioning the model onto so many devices is not an easy job. We observe that in data parallelism, parameters are replicated on every worker. In an optimization step, the gradients are first synchronized over an all-reduce operation. Then, element-wise computation is performed over the gradient, the model parameters, and a few optimizer states. This creates the optimized new model parameter for the next iteration. We are inspired by Zero Optimizer, another state-of-the-art system that can reduce up to 75% of memory footprint. The core idea is that, as it is well known, an all-reduce operation can seem as a reduce-scatter operation followed by an all-gather. When the gradients are synchronized using reduce-scatter, on every worker, we only have a small portion of the globally synchronized gradient, and then each worker only updates its relevant portion of a model parameter. Finally, the new model parameters is ready for each worker after the all-gather. The optimizer states occupy the largest amount of memory, and now they can be partitioned, because only the parameters are needed for the next iteration. As a result, the memory footprint is greatly reduced. This idea is purely for data parallelism. To adopt it with our hybrid parallel strategy and scale to tens of thousands of processes, further customization is needed. We call our optimizer Parallel, a parallel partition-based optimizer. We employ a hierarchical partition strategy for global synchronizations. And for experts that are replicated within nodes, they are partitioned following the aforementioned way. As shown below, each column represents 4 replicas of an expert. A reduce getter operation is first performed to have part of the synchronized gradient on each worker. Then update over the local quarter of the parameter are performed on every worker. Finally, an algetter is used to let every worker have the updated parameters. For non-MOE parameters that require global synchronization, reduce getter is only performed within a supernode. Then, across supernode, all reduce operations are used to synchronize every quarter of the gradients. After that, it is similar to the update process for experts. This can efficiently avoid the expensive collective communication operations with 100,000 processes involved, and the volume of cross-supernode communication is minimized. The third challenge is about mixed precision training strategy. Mixed precision is commonly used in pre-trained models, benefit from low precision data types including FP16 or BF16. Mixed precision training can achieve higher performance and lower memory footprint. On Sunway supercomputer, FP16 performed 4 times faster than FP32, significantly affecting the training performance. There are some existing strategies for mixed precision training, but they are not designed for such an extremely large-scale model. We take NVIDIA Apex as an example. Conservative strategies such as O0 or O1 shows low performance on Sunway. However, aggressive strategies such as O2 and O3 are hard to converge. So, we need a mixed precision strategy that guarantees both performance and accuracy. We observe that different layers in the model have various computation patterns. So, we can use different mixed precision strategies on different layers. By evaluating the convergence with small-scale model and verify on large-scale model, we propose a layer-wise strategy. We use Apex O0 on the embedding layer, O1 on the attention layer, and O2 on the FFN layer. The evaluation shows that our strategy can converge as Apex O0 and O1 did, while O2 cannot converge. Furthermore, our strategy has significantly higher performance. The fourth challenge is the load imbalance on MOE models. On each node, the input data will select experts for computation. After the all-to-all communication, different experts will receive different amounts of inputs. The evaluation shows that the most popular expert will receive over 50% inputs, which lead to serious load imbalance and hurts MOE's performance. Considering the token distributions on the experts are unpredictable, we should use a strategy that can not only balance input tokens, but also be light-weighted. So, we propose swipe strategy. Swipe will swipe the imbalanced tokens with few communications and lead to perfectly balanced without discarding any tokens. The fifth challenge is from Sunway architecture. The new generation Sunway uses a heterogeneous architecture. A Sunway CPU makes up 6 core groups. We call it a CG. Each core group contains a management processing element, MPE, and 64 computing processing elements, CPE. Each node has 96 GB of main memory. A common usage on Sunway is to place one process on each CG. In this way, communications between CGs are using NIC. Meanwhile, when we scale on the entire supercomputer, there will be about 600,000 processes involved, which will hurt the performance of computation, communication, and I/O. To settle this problem, we use one process on one CPU. In this way, communications between CGs are using shared memory, so we can use one thread to handle an MPE and all the CPEs. The other 5 MPEs can be used to handle the communications or I/O. Due to the time constraints, we did not expand to explain other optimizations, such as memory optimizations, numerically stable computation kernels, data loader, and checkpoint. For more details, please see our paper. As a result, we proposed our system. We named it BAGUALU, which is the name of a magic stone in ancient Chinese mythology. BAGUALU can generate efficient medicine, which refers to the neural network models. BAGUALU is the first work scaling a pre-trained model to brain scale with 174 trillion parameters. Our system scaled a model training on an entire supercomputer with over 1 EFLOPS performance. For the experiment, we used a multimodality model for our evaluation. The model is based on Alibaba M6. For an input with image and text, the image patches and tokens will be embedded. Then concat as the input of the transformer model. We used a multimodality dataset M6 corpus, which is about 2 terabytes from many fields, including encyclopedia, web pages, and e-commerce. We scale BAGUALU on the entire Sunway supercomputer with 96,000 nodes and over 37 million cores. The evaluation shows that for the model with 1.93 and 14.5 trillion parameters, BAGUALU can achieve over 1 EFLOPS mixed performance. For the model with 174 trillion parameters affected by global communication, BAGUALU shows lower performance with over 230 pFLOPS. On the 1.93 trillion parameters model, our system shows a clear convergence trend within 500 steps, verifying our system's correctness. We evaluate the scalability of BAGUALU. With 1/16 to the full system of Sunway supercomputer, for weak scalability, BAGUALU shows the speed up of 14.9 times and 14 times with single and mixed precision. For strong scalability, BAGUALU shows the speed up of 12.5 times and 11.3 times with single and mixed precision. The experiment proved that BAGUALU has very good scalability. To meet the challenges of such large-scale pre-trained models on such a large-scale supercomputer, we propose a hybrid MOE and data parallelism strategy for parallel strategy, a parallel partition-based optimizer for model partition, a layer-wise mixed precision strategy for mixed precision training, the swipe strategy for load imbalance, and intra-node optimizations for Sunway architecture. To summarize up, we propose BAGUALU. The first work scales a pre-trained model to a brain scale with 174 trillion parameters. We scale model training on an entire supercomputer with over 37 million cores and achieve over 1 EFLOPS performance. This is an unprecedented demonstration of algorithm and system co-design on the convergence of AI and HPC. Thank you very much.